this is now a follow-up to the slides where I explained name binding and mutability. So now we'll see the concrete examples and we'll work through them a little bit more. The first thing to observe is, as I said earlier, that an object can have several names. So here I define an object, and the object in memory will be 2, and I give it 2 different names, or 3 different names actually. I name it A, or I name it B, or I name it C. So if you look at A, B, and C, they all refer to the object 2. So remember, we said that the name is bound to the object. Now, once you have a name, you can ask for the ID of the object that that name is pointing to. And this is what ID does. So ID gives you a place in memory where the object is stored. And here you get a long integer or an integer, but it might be easier to read if it's in hexadecimal. So this is how you get it. You convert it to hexadecimal. Now, we have the objects A, B, and C in memory, and we can test whether the IDs are the same. So we will check this here, and the answer is true. So the ID of E is equal to the ID of B and is equal to the ID of C. Now, this is something we might do frequently if we're doing some kind of programming or in a particular type of programming to check whether 2 names refer to the same actual object. So to test this, there is the operator is that you can use as well, and this does exactly that. It calls for the ID of A, the ID of B, and checks whether the 2 are equal, for instance. So this works for simple objects, but it also works for more complicated objects like lists. So here is an example where I construct a list with the numbers between 0 and 4. I construct a second list by saying, I assign a second name, second list, to the same object. So if I print second list, I indeed get 0 to 4. And then I can ask for the ID of second list, which is the same actually as the ID of first list. And this is indicated here with is. Okay, so I've told you so far about the distinction between mutable and immutable, and let's see this precisely in the context of the memory locations. So here I'm taking B and I'm comparing it to B plus 1. So the object B plus 1 in memory is created, and this has a certain ID, and then I'm comparing it with the ID of B, and in this case you see that it's false. Similarly, if I do something slightly more fishy, so I take C, take its ID, and then modify it in some way. And C was an integer, so as soon as I modify, Python creates a new object in memory. So the ID of that object has changed. And you see that those 2 IDs here and there are actually different. Okay, but this is for an integer, and it would be the same for strings and tuples. But for lists, it will be different. So let's see that now. I have a first list that I've already defined before, and I'll ask to print this ID first, and this is here. And then I modify the index 0 entry of first list to 17. I reprint it, so this has changed. The 0 is changed into 17. And I ask to print the ID. Now, the value of the object has changed, but no new object was created. It's still the same ID that hasn't changed. And that's the main property of lists, or that's what we insist on here, is that they are mutable. So their ID will not change here. And the point is now first list and second list, they're still pointing to the same object. So if we compare them, if we do first list is second list, then we get true. And if we print second list, we see that second list has changed. Now, I said if we compare them, let's make sure we understand what is meant here. What we're doing is we're comparing the object in memory. We're not really comparing whether 2 lists contain the same thing or not, or we're really comparing whether they are the same object in memory. And the answer here is true. So you can do the same thing with appending and a lot of different operations on the list. So here is a few examples. So here I have a list that I define, 5, 7, 11, and I take its ID, and then I modify it in a variety of ways, and you see that the result changes here. But the point for this presentation here is that the ID hasn't changed because the list is mutable again. Okay, so there is a lot of danger associated to that if you don't really understand it. So the danger is that you have two different names pointing to the same object, and you modify the object by accessing via one name and not the other, and the consequence is that some object changes and you didn't expect it. So let's see the cases first where this does not happen, because we have immutable objects. So each time an object, we're trying to do something with an object, we have to create a new one, and we avoid this problem. So this immutable cases, again, it's ints, strings, tuples. So let's see that. So we have here we assign A to 10, we print A, we assign B to A, we modify A, we print A has changed, but B hasn't. Okay, so this is similar to some examples that I had in the slides. And integers are immutable, so are lists. So if I do the same thing with lists and use augmented addition, so concatenation, I go from foo to foo bar, and here is the result. Now for lists, it's a bit different because lists are mutable. So again, let's see this example where I modify A by appending 1. And so far, everything is like you would expect. And then I would ask you, what is happening with B? Has B been modified or not? And the answer is that B will be modified because B and A are pointing to the actual same object still. Okay, so this is for plus equal, which means modify A by adding 1 to the end. And here we see a slightly different example. So we're using different variable names because now they're capital. And we see that we're doing a slightly different operation here. We're creating a new object by appending A and appending 2 to A. And this is a new object, and we're assigning A to this new object, or binding A, the name A, to this new object. We're not changing which object B was pointing to, so in the end B hasn't changed, or the value of B hasn't changed, but the value of A has changed. So you should really compare the outcome here to the outcome here, and that's the main point here. The difference is in this operator versus this operation. Okay, so here is yet another example with appending. So if I append, you see that B has changed and B has tracked the changes that A had. So A and B are still pointing to the same thing. Okay, so I think I've insisted enough on all this. Let's see some actual other source of confusion. Well, it's still related, but it's a slightly different problem. So here it is. So we are going here to compute, to roll a die over 20 consecutive days and record on which day each number appeared. So I roll the first die, record that on the first day this result happened, second day this result happened, and so on. And the way we're doing it is we're maintaining a list of results, and it will be first empty lists for every day, and for every possible result, sorry, not every day, every possible result. So there are 6 possible results, and for the days in range 20, so between the 0th day and the 19th day, what I will do is I will use the random module to pull out a random integer out of my hat between 1 and 6 uniformly, and this will be position. So this is the roll of the die, if you want. Maybe it might be better defined to be roll, and here the result of the roll. So the results will be recorded in that position, so that day will be recorded at that index roll. And since we're rolling a die, it's really natural to take roll between 1 and 6. That's why I'm using here rand int between 1 and 6. And that's also why, if you look here, I have 7 times the empty list, because I want the indices to be between 1 and 6. So I'll add a dummy index 0 at the beginning that I don't intend to use. So, okay, you should really think at this stage what is meant to happen here, and whether this will really perform like we want. So now we have somehow the variable results in memory. And what is the results? Wait a minute, the results is 7 times exactly the same list, and that list is all the days between 0 and 19. This is obviously not what we wanted. We wanted to have a list where the first entry would be an empty list, and all the others would be splitting up all the integers between 0 and 19, depending on which roll of the die happened when. So why did this happen? Well, this happened because we defined the results, the initial results list, the list that would collect all the answers, in this way. So we said construct the empty list and then take 7 copies of it. But it's actually not 7 copies of it, it's point 7 times to the same empty list. That's really what happened here. We're pointing 7 times to the same empty list, and what we're doing here is assigning to the third entry, say, we're adding a day at the end of the third entry. But this third entry happens to also be the second or the fifth entry. So every day we're modifying all the entries and adding the day at the end. And this is not really what we wanted. So a slightly better way to do it would have been to do it this way. So instead, we should have used results equal, and now it's a different list for every integer between 0 and 6. And then we do the same thing. So here is the program that we get. We run it, and we see that the print results returns something we expect. So here it means that on the 17th day, I rolled a 1. And on the 18th day, I rolled a 6. So you see that all the days are properly split up, and none of them are a 0. I've never rolled a 0, of course, with a die. So that's really the behavior we're hoping for, and this behavior here was wrong. And the reason, again, is that this assignment here is not the same as this assignment here. So for all those things, if you don't really understand the difference, I really suggest you enter those lines into Python Tutor to see what happens at every step. So this is an example with the roles of something that can be problematic with nested lists, or can be confusing. So here is another example where I give actual names, so it might be a little bit easier to understand. So I take data to be the string, the list of strings Albert and a koala, and then nested will be a list consisting of twice the list data. And then I modify data in some way. I replace koala by kangaroo, and I print data, and data has been modified. Now it's Albert and a kangaroo. But if I print nested, now I have 2 lists like I expect, but those 2 lists are the same. So I've actually modified both of them at once. And if I was to modify it in some other way, for instance, I take the second part and add a 5 at the end, then I also modify the very first one by adding a 5 at the end. Okay? So if this behavior is not the one you want, you can instead ask for a copy of the list. So to make sure you really produce different things here. You don't have nested point twice to the same link, but to the same list, but point to 2 different lists. And in order to do this, you can do it this way. You can ask here for nested to be pointing to 2 copies of data, 2 different copies of data. So if you print nested here, you see that both copies are indeed Albert and a koala, Albert and a koala. And then you assign to the second entry of data kangaroo, and you print nested, and neither of the 2 has changed, because so nested hasn't changed. The reason is that nested is not pointing to data. Nested is pointing to copies of data that haven't been changed. And if you only change one of the 2 parts of nested, you change like this sublist, or actually you replace the koala here by kiwi, which is what we're doing at this step, and you print nested, then you see that nested consists of two sublists, Albert and a kiwi, Albert and a koala, and they haven't tracked each other. Indeed, they were originally assigned to two separate copies of data, and they are just separate objects in memory. So again, this subject can be a bit confusing. It's probably a bit early to see this in week 3 of a first programming course, but I think it can lead to a lot of confusion if I don't explain a potential sort of the problem, because the behavior is maybe unexpected. So I mean all this information about name binding and mutability to be really a warning for potential problems that will happen at some point. And probably you didn't understand everything now, but when those problems occur and you have a bit more familiarity with lists, you might want to look back over those lessons and try to make more sense out of them. And it's essentially those lessons here now are preventive of those problems.